Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning, everyone. Today we will examine heat transfer mechanisms and focus specifically on the three fundamental modes of heat transfer, which are conduction, convection, and radiation. I will describe the physical principles governing each mode, give practical examples, and point out how engineers model these processes for design and analysis. Let us begin with conduction. Conduction is heat transfer within a material or between materials in direct contact due to temperature gradients. At the microscopic level, energy is transferred by vibrating atoms and free electrons in solids. Fourier's law provides a quantitative description of conduction. It states that heat flux is proportional to the negative temperature gradient and to the material's thermal conductivity. So a high thermal conductivity means faster conduction. A concrete example is a metal cooking pan. When you place the pan on a stovetop, the metal rapidly conducts heat from the flame across the pan. Because metals have free electrons, their thermal conductivity is high. I use the example of a metal cooking pan to show that conduction depends on thermal conductivity and the temperature gradient. Contact resistance is another important issue in conduction. When two surfaces touch imperfectly, there are microgaps that reduce heat transfer. Engineers often model thermal resistance at interfaces to predict temperature drops across joints. Next, we turn to convection. Convection involves heat transfer between a solid surface and a fluid in motion, or between different parts of a fluid driven by bulk motion. Free convection occurs when buoyancy forces move the fluid, because warmer fluid is less dense and rises. Forced convection happens when an external device like a fan or pump moves the fluid. This is the dominant mode in many engineering systems such as heat exchangers and building HVAC. In practice, convective heat transfer is often described using Newton's law of cooling, which uses a convective heat transfer coefficient multiplied by the temperature difference between the surface and the bulk fluid. That coefficient encapsulates fluid properties, flow regime, and geometry. To predict convective behavior, engineers use dimensionless numbers such as the Reynolds number and the Prandtl number. These help determine whether flow is laminar or turbulent and are used to estimate the Nusselt number, which gives a convective heat transfer coefficient. Consider the example of a radiator in a car. The coolant transfers heat by conduction through the metal fins, and then by forced convection to the air blown by the fan. Increasing surface area and creating turbulent flow increases the convective heat transfer rate. Finally, radiation is heat transfer by electromagnetic waves and does not require a material medium. Radiation becomes important at high temperatures and in vacuum, where conduction and convection are absent. The Stefan-Boltzmann Law relates the radiative heat flux from a surface to the fourth power of its absolute temperature multiplied by emissivity and the Stefan-Boltzmann constant. Surfaces with high emissivity radiate more effectively than low emissivity surfaces at the same temperature. A practical case is space engineering. In spacecraft, thermal control radiation is the primary mode to reject heat into space, since there is no air to convect heat away. Another example is building design. Windows lose heat by conduction and convection, but also by radiation. For low emissivity coatings on glass, reduce radiative heat loss and improve thermal performance. Often, all three mechanisms act together. For instance, a wall system experiences conduction through solid layers, convection at the interior and exterior surfaces, and radiation across gaps. Insulation and surface treatments are ways to manage these different resistances. When analyzing systems, engineers construct thermal resistance networks combining conductive, convective, and radiative resistances. This approach helps compare contributions and identify which mechanism controls the overall heat transfer. In summary, understand the governing laws for conduction, convection, and radiation. Recognize real-world examples such as pans, radiators, and spacecraft, and use models like Fourier's law, Newton's law of cooling, and the Stefan-Boltzmann Law to quantify heat transfer. That concludes the lecture on heat transfer mechanisms. I will now take questions.
Listen again to part of the lecture. Then answer the question.
I used the example of a metal cooking pan to show that conduction depends on thermal conductivity and the temperature gradient.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.